All right, everybody, welcome back. We are going to continue on with our Unit 1, which is Waves and Oscillations. This is going to be PowerPoint Section 4. So this topic is going to be covering things like waves on a string, which we've started talking about previously, and then we're going to talk about how some instruments work, in particular string instruments and wind instruments. All right, so let's jump back in. And like I said, this is the Waves unit on strings and instruments. So the first thing we're going to do is we're going to watch a short video clip. Okay, and this is on Lego. Give me a second to set up and running. And so this is a video clip where he's talking about some of the history. This was discovered about 4 years ago. So here we go.
Tremendously exciting news. Gravitational waves have finally been detected. Here's a brief explanation. Back in 1915, Albert Einstein gave the world his new theory of gravity, the general theory of relativity, which is based on the beautiful idea that gravity is nothing but warps and curves in the fabric of space-time. Now, barely a year later, Einstein pushed this idea one vital step further. You see, he realized that if space is flexible enough to warp, then it should also be able to ripple, to vibrate, to undulate. And that would mean that if something were to jostle the fabric of space-time, it should send out ripples in the fabric of space, and it's those ripples that we now call gravitational waves. Now, of course, the source of gravitational waves would not be my hand jostling space. Instead, it would be some highly energetic astrophysical process like rapidly orbiting neutron stars or black holes that would send out a steady rumble of gravitational waves. Or at least, this is what the theory says should happen. Now, how do you test this idea? Well, the math shows that as a gravitational wave rolls by, it will squeeze and stretch anything in its path. You see it happening here for the Earth, but of course, this is highly exaggerated so you can see the effect. When you do the calculation, you find that the amount of squeezing and stretching would be tiny, a mere fraction of an atomic diameter, and that makes it pretty difficult to detect. But that is what the LIGO team has now achieved. And they did it with two detectors, one in Louisiana, the other in Washington State. And in these detectors, what they do is they fire laser beams along two 4-kilometer-long evacuated tunnels. And when the light recombines, it creates an iconic pattern. It's known as an interference pattern. But the only thing that you need to grasp is that were a gravitational wave to roll by, it would squeeze and stretch the arms of the detector, and that would have a measurable impact on that interference pattern, causing it to shift. And it's just that kind of shift in the interference pattern that the LIGO team has now observed. The first direct detection of gravitational waves. And this is big. This will go down in the history of science as a pivotal moment. And not just because it's another spectacular confirmation of Einstein's ideas, which it is, but rather because for millennia, we have explored the universe using waves of light. This discovery marks the opening of a new era in which we will explore the universe using waves of gravity. Tremendously.
All right. Let's go back to our PowerPoints. There it is. All right. So, LIGO, we said the waves were first detected in 2016. So this is about 4-year-old data. Einstein had proposed this stuff about a little over 100 years ago. It took him about 100 years to find it. So this is made up of what they call an interferometer. An interferometer has light that travels along 2 different paths, or waves of any sort travel along 2 different paths, and then they recombine. We're looking for interference patterns. So this particular interferometer has 2 arms. One arm is right here, and the other arm runs perpendicular to it. And there are mirrors hanging at the ends that move ever so slightly as the gravitational waves pass. And that creates an interference pattern. And there are two of these at the detectors. LIGO has one in Louisiana and one in Washington, so they're spatially quite far away. There are a variety of other detectors around the world. There's some in Europe, there's some in Asia, all around the world, but they're also trying to pick up the signal. Okay. So a light beam shines out, comes down one arm, hits the mirror, and comes back and hits, this is probably a partially silver mirror, something along this line. So it comes down, hits the mirror, reflects back, and then hits the screen. At the same time, another beam of light will come, hit the detector, or hit the partially silver mirror. It'll come through, come back, and recombine on the screen. And so they'll have the initial configuration set up so it's either fully destructive or fully constructive. And then what happens is as the wave passes by, one or more of the mirrors will sway ever so slightly, like a very, very long pendulum, ever so slightly. And it changes the path length ever so slightly. And by changing the path length, we change the phase at which the light hits the screen. And by looking at that change in phase, we now will get bright and dark signals on the screen. And so the screen will have some kind of a detector on there, some kind of photodetector that will measure the intensity of the light that hits it. Okay, so like we said, if we have two waves that add up and they are exactly out of phase, so apparently this detector is set up with a no light condition initially. So two beams come through, they recombine on the screen such that they're 180 degrees out of phase, and so we have no signal at all. When the gravitational wave comes by though, it will cause it to move ever so slightly, one or both. And if you notice in this one, A does not change its phase, but B has shifted its phase ever so little. And now we add these two together, notice we get constructive interference that is no longer a zero signal. Okay, and so this is the real data from the very first signal. Remember, this was data that Einstein proposed over 100 years ago. The National Science Foundation had been funding this research for well over 30 years before they got their first piece of data. And there is two signals, one from Hanford and one from Livingston. So the two sets of data, that each one is independently recording its own data. And the light lines on both of the narrow lines are the predictions, and the blue lines, or the thick lines are going to be the actual data. And so both sites recorded data. Both sites matched the predictions well, but more impressively, look at these two sites. Especially when we get to the stronger parts of the signal, they line up almost exactly the same, which gives us a good indication that it was something that was happening to the entire Earth rather than a truck driving by. Or even something as localized as like an earthquake or something that made one of them sway and the other one not. We would not see the same signal line up exactly the same as well as it did. Okay, so this was the first data. They've been waiting many, many years. Many people working on the project for a very long time. This occurred right after they upgraded their system. They increased their system by a factor of 2. They brought it up and running like December, January, and by February they had maybe upgrading. But anyways, within a month's time of upgrading it, they were able to get their first signal. And shortly thereafter this, they were able to find the next signal that they've had multiple signals since then. Okay, so let's transition. And this problem is mostly a review problem, okay? So take a moment and read this problem. And what I would like you to do is write down everything that this problem tells you. So make your lists of known unknowns before we start working on this one as a group. So take a moment, pause the video, and start making your list of knowns and unknowns. And figure out what's happening too. All right. So example 1.33 nodes on a string. And the first question is, what is the node spacing along the resulting wave, standing wave? So first off, what is a node? Okay, remember a node, if I have a wave doing something like this, our nodes are these points where we're at 0. Okay, so we want to know the spacing, say from here to there. Okay, so we start reading this problem. It talks about things like linear density. What symbol do we use for linear density? So mu is equal to 5.0 grams per meter. Okay, it also tells us our tension T is 8.0 newtons. Our frequency, 100 hertz. And our amplitude, I'm just going to call it capital A, is 2.0 meters. Okay, make sure as you read through that, you can identify all of those parts. Okay, so the first part asks us about our node spacing. So our spacing we saw is this point between two zeros, which we know if we look at our picture, the space between here and here is one full wavelength. So space between our two nodes is going to be half wavelength. So we want to find, for part A, we're going to find 1/2 lambda. So to find 1/2 lambda, we're going to have to find lambda. Now, think back to what we did before break. And among the things we had was relating things like velocity, frequency, and wavelength. So we know that velocity of our wave is equal to the frequency times the wavelength. We want to find our velocity, our wavelength. It told us our frequency. So if we knew our velocity, we'd be able to find our wavelength. Now, when you start seeing things like linear densities and tension showing up, your mind should go to the fact that we probably are going to be adding things like, or finding things like velocity. And in fact, we do know how to find velocity. Velocity is equal to what for a wave on a string? Take a moment, look it up. Pause the video if you need to. Okay, velocity is equal to the square root of tension or the linear density. Remember, we have to convert everything to standard units, which means you have to convert your linear density. So when you do that, you're going to get tension is equal to the square root of tension, which is 8.0 newtons. We do not have to change that one over. We do have to convert our linear density, mu. Mu, we said, is 5 times 10 to the negative 3 kilograms per meter. Make sure you do that conversion and make sure you get the same number. Okay, go ahead, take a moment, pause the video again, and go ahead and do that calculation. When you're done, if you're working with a buddy, compare your answers. If you're not working with a buddy, then continue on after you have your answer. Hopefully you will get 40 meters per second. Okay, so now we know how fast our wave is traveling. We're traveling at 40 meters per second. We know our frequency is 100 hertz. We can solve for our wavelength. So our wavelength, lambda, is going to be, solve this one for lambda, so we're going to have V over F, which is going to be 40 meters per second divided by our frequency of 100 hertz. And when you do that, you should get 0.40 meters, which is going to be the same thing as saying 40 centimeters. Okay. If you have questions about this, please remember, shoot me a message, post a question on Discord or on our discussion chat. We have a live chat box in there. We have a discussion where we can do asynchronous chatting. please, guys, post your questions, post your concerns. We'll figure this out as a group. I guarantee you there are no stupid questions. Everybody in the class is trying to figure this out together. I'll be honest, I'm trying to figure out how to do this together in the best way also. It's very different than teaching in the classroom. We're going to figure this out as a group, so don't worry too much. This will all work out okay. Now, part B, maximum displacement. So, we're talking about standing waves, right? And if you recall standing waves, we essentially have one wave that's traveling one way, and the other wave is traveling the other way, right? And these two waves are going to meet. Sorry, I'm running out of space. These waves are going to meet. And so when these two waves meet, they're going to be added together. So if we have constructive interference for part B, what has to happen to their amplitude? If you say they have to be added together, you are correct. So our max displacement is going to be equal to twice the amplitude. And we said our amplitude was 2 millimeters. So our max amplitude is going to be 4.0 meters because they're going to add together constructively. Okay. Any questions about this one so far? Okay, I think we're about at the end of our time for our first one, so we are going to stop here, and then we'll start a new video picking up right where we left off.